In this lecture video, we will take a look at the Lewis model. Please read the OER textbook chapter 6.1 for more details. In the previous lecture video, chapter 5, we covered the different type of chemical bonding, including ionic bonds and also covalent bond as well. In this video, we are going to take a look at within those bonds, how each atom are connected between each other, and that can be described by the Lewis model. Okay, so the homework that associated with this chapter section is the paper homework 6.1 that will be posted on Moodle. And I'm going to break this chapter 6.1 into 3 different parts. The first part of the lecture 6.1 would be in this video. And after you finish watching this video, you should be able to start working on part A, number 1 to 5. And then for the second video, which is going to be 6.1 part 2, you should be able to start working on number 6 to 8. And then the last 6.1 part 3 is going to be cover the homework number 9, 10. Okay, so pretty much the theme of chapter 6 is we are going to take a look at how the atoms are connected between each other by using the Lewis model to help us see the connection between each of those atoms. And also we are going to look at the shape of the molecules as well by using the different type theories that we are going to look at later on in the following videos. The Lewis dot structure represents the number of valence electrons on an atom. Those non-valence electrons or the inner core electron will not be included in the Lewis structure. For example, let's start with the simplest type of Lewis structure that describe for just atoms. Okay, so for example of these atoms, in order to represent the Lewis structure for each of these atoms, we are going to include only their valence electrons. Okay, so how do we find their valence electron? That's when we will need to look at the periodic table. Okay, so the periodic table, especially with the main group element, will tell you their location on the periodic table will tell you about their number of valence electron. For example, magnesium, aluminum, oxygen, and nitrogen here. I'm going to circle those. So we have magnesium, aluminum, oxygen, and nitrogen. We will see that those are on the main group element, and each of those are located in the different group. For example, magnesium is in group 2. Group 2 indicates that magnesium should have the number of valence electron equal to 2. Okay. Group 3 indicates that aluminum would have its valence electron equal to 3. And nitrogen group 5 would have its valence electron equal to 5. And group 6, right, so 6A would be number of valence electron would equal to 6. Okay, so that's why if you keep continue looking at, right, all the way to group 8A, we know that the noble gases would contain 8 electron for the outer shell electron. So that's why later on we are going to see the octet rule, because these octet or these 8 electron as the outer shell would be the most stable electron configuration. So that means pretty much everything want to achieve that, right? So which is going to be the most stable electron configuration for that. Okay, so according to this, we see that magnesium has 2 valence, aluminum has 3, nitrogen has 5, and oxygen has 6. So if you put this into the Lewis dot structure, you can put 2 dot for magnesium because this is neutral. It has not lost electron yet. So therefore, you are going to include those 2 valence electron around magnesium neutral atom. Another way to write these can be magnesium, and then you can put 2 dots together as a pair of electrons. So that's okay as well. Okay, and because aluminum is in group 3A, so there will be 3 valence electrons. So you put 3 dots that represent the 3 valence electron for aluminum. And same thing for oxygen as well. This is neutral atom, therefore there will be 6 valence electron for oxygen, so you can put them 6 of them, right? So you pair them and then you can have them as an unpair. And then the last one would be nitrogen, which is group 5, that would contain 5 electrons. Okay, so again we are looking at only the valence electron. Okay, so the valence electron only that will be represented in the Lewis dot structure. Any other electron will not be included, right? So the inner core electron will not be included because those will not participate in the chemical reaction. The only thing that participates in the chemical reaction would be the outer electron, similar to an example that I mentioned in the previous video that talk about gobstoppers, right? So when you suck on gobstopper, the color that change first is the outer layer, right? So same thing for an atom as well. So whatever going to undergo chemical reaction would be the outer shell of the electron. So therefore, in this case, we are going to represent just those that would undergo chemical reaction. Next, we are going to take a look at how to draw Lewis structure for the compounds. Before, in the previous slide, you see only just the single atom. So now we're going to put those atoms together in a compound, and we're going to see how they connect and how they are sharing electrons. Okay, so the two rules that we are going to use, one is the duet rule. Duet rule is going to represent only two elements. One is the helium, the other one is hydrogen. So pretty much because helium is one of the noble gases that is stable, so helium has only 2 electron maximum. Therefore, the another atom that is going to be close to have the same number of electron, valence electron as helium would be hydrogen. So that means hydrogen will not have more than 2, right? Duet is 2. So that means in this case, this 2 is going to be the one that cannot have more than 2. Okay. More than 2 electrons. Okay, so everything else we are going to follow the octet rules, which mean that pretty much all other element would most likely to have 8 valence electron total. So that means in order to make the compound that is stable, you will need to make sure that each element will need to have their surrounding number of electron equal to 8. That's what it means, right? So we are going to have to achieve this octet rule. That's what it's referred to, because again, octet is represent the stable electron configuration for the noble gases. So that's why we are going to apply that to other elements as well, that they are going to most likely to lose or gain electron or share electron in order to achieve the stable electron configuration. Okay. So I'm going to start with the first type of compound that we learned, because we learned 2 types previously. We learned about the ionic compound, and we also learned about molecular compound, right? Those two have different type of bond. Ionic compound would have the ionic bond, which means that the electron is already completely transferred from one atom to another. But for molecular compound, it's going to be sharing electron between 2 atoms, so they are a little bit different. How we draw the structure to represent what is going on would be different, right? So in this case, let's take a look at the ionic compound first. Okay, so the one that we're gonna take a look at would be example 5. We're gonna look at all of these ionic compounds that contain metal and non-metal, right? So ionic compounds come from metal and non-metal. So pretty much what you are going to look at is, because we are going to look at how the electron is transferred, because the atom have to become ions, right, in ionic compound. So which means that we're gonna start with something that is going to start with just the single atom, so that way you see how electron is actually being transferred. I'm going to look at sodium and chlorine. Okay, so if you're looking at sodium and chlorine, okay, sodium is in group 1, chlorine is in group 17 or group 7A. So that means the valence electron of sodium would be 1, and for chlorine would be 7. So if I draw Lewis dot structure of the neutral atom of sodium and also the neutral atom of chlorine, what I would get would be 1 sodium of the valence electron around sodium, right? And then 7, 1, 2, 3, 4, 5, 6, 7. So I actually highly recommend you actually put them as a pair first, because if you think about it, when you draw the orbital filling diagram, right, the electron come as a pair, whether they spin up or spin down, right? So they come as a pair. So that's why I'm actually drawing this as a pair right here. Okay, so what we can do next is that this is not the ionic compound yet, because electron has not transferred. Okay, you do not make a bond between these two. The reason for that is because if you connect the 2 dots together, it means that the 2 dots are sharing. This is not sharing electron according to the ionic bonds definition, right? The electron must transfer okay, between the two atoms. So in this case, if you're looking at the periodic table, we know from the previous chapters as well, chapter 4, we know that sodium is going to be bigger than chlorine, right? So because with the same number of energy shells, right? You can compare the effective nuclear charge. As the chlorine has a bigger nucleus, it's going to have higher effective nuclear charge, which means that the outer electron would experience a stronger attractive force from the nucleus. Therefore, in this case, chlorine would hold its electron like tightly, right? Compared to, so the size of chlorine would be smaller than sodium, okay? Because sodium is bigger, so that means the outer electron would be lost easily. So that's why the electron would transfer from sodium to chlorine. Okay, because it's easier to transfer from metal to non-metal because of that. We already learned this in chapter 4. Okay, so I'm going to tie that back again here. Okay, so that means in this case, this one electron right here would completely transfer. Electron would move from sodium to chlorine. Okay. When electron in the sodium move to chlorine, now sodium would have only is already have the 8 electron outside, right? Because if you think about this, as it lost one here, as it lost one here, right, it's going to have the same number of electron as neon. So that means it's already achieved the stable electron configuration. So therefore, in this case, you don't need to specify any electron around sodium at all, but you will need to specify its charge, right? Because sodium already lost 1 electron, therefore the charge of sodium would become +1, right? Because it lost 1 negative. So it's going to become a positive value. Okay. Chlorine, okay. Because chlorine is gaining 1 electron, so 1, 2, 3, 4, 5, 6, 7, right? And then it's gaining 1 more from sodium. So now the total number of electrons for chlorine would be 8 now, right? So you are going to use the bracket, right? And then represent negative. Okay, so to indicate that this is overall, chlorine is the one that accepts the electron, right, become an octet as well, and is going to have a negative charge because it accepts 1 electron. Okay, so what you are going to do is that you will need to show for the anion, you always need to show the 8 electron is always going to achieve this 8 electron. For cation, you don't need to show anything because it's actually going to refer to the same number of electron as noble gas without showing any dot for the cation. So again, for ionic compound Lewis dot structure, cation would have no electron dot around it because already completely transferred. But the anion is going to be the one that would achieve it will have the 8 electron around it. Okay, so but both of them will actually, if you draw out the electron configuration for both of them actually have the same number of electron as the noble gases. Okay, the valence electron, sorry. So now let's take a look at K2O. Okay, so what about K2O? So subscript 2 is indicated this formula unit right here contains 2 potassium and 1 oxygen. If you look up on the periodic table, potassium and oxygen, you will see that potassium is in group 1 again, and then oxygen is in group 6. So we have 6 electrons for oxygen as the valence electron, and then 1 for potassium. So 2 in ionic compound is represent like this. Okay, so we have 2 potassium and we have 1 oxygen. Okay, so that's what it represents here. And each potassium contains 1 electron and oxygen contains 6. Okay, so again, because potassium has a bigger size than oxygen, therefore potassium is most likely to lose electron, right? And it's also easier to lose this 1 electron as well, right? Because it just have 1. So that means in this case, the electron on potassium would transfer to the oxygen. Okay, so therefore potassium would be potassium 1 plus, right? Each of these potassium would be potassium 1 plus, but because we have 2 of them, so that 2 potassium now would become in front of it. Is indicate that this ionic compound would contain 2 potassium ion. Okay, so that's what it means. And oxygen now is going to have 8 electron. Oops, sorry. Let me color code this. Oxygen now is going to have, 8 electron around it too. Okay, so 1, 2, 3, 4, 5, 6, and then 2 more, 7, 8. Okay, come from potassium. And again, because oxygen received 2 electrons, therefore the overall charge of oxygen ion now would be 2 minus. Don't forget to use bracket and also indicate the charge for that. Okay, so again, if you go back here, as each potassium lost 1 electron, you will see that it's going to achieve the same number of valence electron as argon. So that's why we don't have to actually represent it here. Okay, and for oxygen, because it accepts those 2, you are going to leave it as 8. Okay, so again, whenever that you see cation in ionic compound, you are not going to include any dot because already indicated it's already lost an electron. And when you see anion, you are going to have to make sure that they will have 8 electron because those electron would come from the metal. Okay. So same thing for calcium as well. Okay, so if you're looking at calcium, calcium is in group 2A. So calcium would contain 2 electrons. Okay, chlorine is in group 7A. So chlorine would contain 7 electrons. So 1, 2, 3, 4. Oops, sorry. Let me actually use different color here. Okay, so chlorine has 1, 2, 3, 4, 5, 6. 7. Okay, so we have 2 chlorine. So I'm going to write out 2 chlorine. Both chlorine contains 7 electrons because they both are in group 7A, right? So that means in this case, again, if you go back here, calcium versus, let me use different color. Calcium versus chlorine, right? So calcium is bigger. It's easier to lose electron than chlorine. So that means in this case, calcium would. Okay, so how many are we going to make it to each of those chlorine? Well, we already see that each of these chlorine contain only 7 electrons. To make it to have an octet, which means 8 electron, it just requires 1 electron from calcium, right? So each chlorine will accept 1 electron from calcium. Therefore, in this case, because calcium lost 2 electrons, calcium therefore would become calcium 2 plus, okay? And because we have chlorine, okay, and each chlorine contains 7 except 1 more would be 8. Okay, so right now it's have 8. Therefore, each chlorine would contain 1 negative charge. Okay. However, if you're looking at this chemical formula, there are 2 chlorine, right? So therefore, in this case, you are going to indicate 2 in front of it, which is going to indicate that this ionic compound would contain 1 calcium ion and 2 chloride ions. Okay, so that's what it's coming from. And this structure that you see here, this is what we call Lewis structure for ionic compound. Okay, so that means if you see any, if you see any ionic compound in the future, pretty much if you don't want to do this, you can just write this right away. Okay, so this is the one that is actually represent the correct Lewis structure. This on this side right here on the left side that you see, it's just how I analyze it or how I show it to you, right? So where are these coming from? It's come from these neutral element that they react, they transfer electron to each other. Okay, so that's what it means. Okay, so for example, if you see, let's say like lithium fluoride, for example, in this case, we know that lithium is in group 1. According to the periodic table that we already learned from the previous chapter, we can also just say it right away that lithium would become lithium plus, right? Because in group 1, it's going to have a positive 1 charge. The reason why it has positive 1 charge, you already see that lithium is going to be bigger than fluorine. So lithium is most likely to lose electron to fluorine, right? So, and because fluorine is going to be the one that accepts electron, so therefore an ion would contain 8 electron total. So you can go ahead, draw those 8 electron right away, and that would represent the Lewis structure. Okay, so again, you don't need to do this analysis. You can just write the Lewis structure of the ionic compound right away. again, to write ionic compound, ionic structure, the cation, which is the metal, would be the charge that you learn, right, from the main group element. Like group 1A is +1, group 2A is +2, and so on. So that's how you get this. The cation will not have any electron dots around it because their valence electron is already transferred. But the anion, you are going to see the 8 electrons surround them. Okay, so don't forget the charges for each of those. And the subscript, right, is going to become the number in front of each of those ions to indicate the amount of ions that we have per ionic compound. All right, let's take a look at example 6. We are going to draw Lewis dot structure to represent the atom of the strontium and phosphorus atom. So in this case, if you go here, this is strontium right here and phosphorus is right here. Okay, so strontium in group 2A would indicate 2 valence electron, right? And then phosphorus would be 5 valence electron. So then I'm going to go back here to answer question A, right? So that means in this case, strontium would contain 2 electrons according to what we saw on the periodic table. And phosphorus contain 5. Okay, so I'm going to do 1, 2, 3, 4, 5. Okay, so B asks, which atom loses electrons and which atom gains electron in the reaction. So if you have these 2 neutral atoms come together, which one you think is going to transfer electron, which one is going to accept electron, right? So pretty much we already know that the metal most likely to transfer their electron to the non-metal. The reason for that is because we already see that metallic character is exhibited by the tendency of losing electron, right? So strontium is more metallic than phosphorus. Therefore, in this case, strontium would transfer these 2 electrons to phosphorus, right? So in this case, if you're looking at this, you are going to see that, well, if it's transfer electron to phosphorus, you are going to see that phosphorus would not contain total of 8 electron, right? So it's going to be only 1, 2, 3, 4, 5, 6, 7. It's going to be only 7. So which means that this is not right. There is something that we need to include here. So the next thing we're going to take a look at is part C. Okay, part C probably help us to write out the Lewis dot structure for this ionic compound better. Okay, so we are going to determine what should be the chemical formula of this product. Okay, so you are having strontium, and strontium, if it's lost electron, is most likely to become strontium 2 plus, right? So strontium would become strontium 2 plus. And if you're looking at this phosphorus right here, phosphorus is in group 5A. So if it's undergo chemical reaction to form ionic bond, group 5A is most likely to form a -3 charge. So that means in this case, we should end up having phosphorus as -3, right? But in this case, we have only 2 negative from just 1 strontium. So that's not going to work out, which means in this case, you first will need to determine the chemical formula that come from these 2 first. Okay. To make sure that the overall ionic compound have to be neutral, what you need is that for these ionic compound that come from strontium ions and phosphorus ion, you will need 3 strontium per 2 phosphorus, right? So because the common denominator is 6, so that means in this case, the correct chemical formula of this would be SR subscript 3 and P subscript 2, right? Because if you think about the overall charge, +2, 3 of them would be +6, right? -3, 2 of them would be -6. Overall, this would be the neutral ionic compound. So that means in this case, in order to analyze this and draw Lewis structure, we need 3 strontium. So that means pretty much it's going to be 3 strontium. Okay, so each strontium would contain 2 electrons. So I'm going to draw 2 electrons. And then phosphorus, we have only 2, right, in this chemical formula here. So therefore, phosphorus would contain 5 electron total. Okay, so each of these strontium, again, going to donate their electron. So this is going to go in here. And you probably notice that if I do it up to this point, each of these phosphorus would have only -2. In order to get -3, therefore, this strontium right here need to give 1 to each of those phosphorus. Okay, so therefore, total charge of the phosphorus would now become -3 because phosphorus now would have 8 electrons, right? So 1, 2, 3, 4, 5, right? And let me actually indicate this in a different color so you see it better. Okay, so 1 is coming from one of the strontium, right, pair electron, and the other come from the other strontium. Okay, so because you have 2 of phosphorus, so therefore in this case we're going to use the bracket, okay, and then indicate that there are 2 phosphorus. And because phosphorus accept 3 electrons, therefore the overall charge of phosphorus would be -3. Okay, and then because we have 3 strontium, we are going to have 3 strontium that contain 2 positive charge. So that means the Lewis structure that represent the ionic compound that derived from the reaction between strontium and phosphorus atom would be this one right here. This is the Lewis structure that represent this ionic compound. Okay, so that's what it means. Okay, so this is going to answer number D for us. All right, so again, for the homework, okay, so what you can start working on now going to be the paper homework part A number 1, and you are going to be able to do these 2 now. Okay, so again, you don't need to do the analysis like I did here. Okay, so if you know right away that you see the anion, you see the cation, which is the metal, right? So give that the charge that is supposed to be, right? And then don't add any dots. For the anion or the non-metal, you are going to make sure that they have the 8 electron around it, and then make sure that it have the proper charge as well, right? So in this case, for example, in this case, potassium and bromine, right? So potassium would be the one that have a positive charge. Bromine would be the one that have a negative charge with the 8 electron around it with the bracket, right? So it's going to be like that. Okay, so you should be able to start working on these 2 examples. I'm going to skip these 3 first, because it contains polyatomic ions. We need to look at polyatomic ions before we can combine them into ionic compound. Okay, so in this case, let's skip those. If you want to pause the video now and start working on these 2 to reinforce your understanding, you are welcome to do that as well. If not, you can just wait until you finish the video to start working on homework. Next, we are going to take a look at the Lewis dot structure for the covalent compounds or molecular compounds that contain covalent bond. So again, the difference between ionic bond is the electron already transfer. So that's why when you see from the previous example, you don't see that I'm making the bond between them, right? They are separate between cation and anion because it indicates that electron transfer from the cation to anion. In this case, electron do not transfer, they are sharing electron. So therefore, we are going to indicate the bond between 2 atoms that are coming together to share their electrons between each other. Okay, so the general guideline to draw the Lewis dot structure for covalent compounds or molecular compound is that we are going to count the total number of valence electron. Again, remember when we talk about Lewis structure, we are focusing on only the valence electron. Okay, so we're gonna have to count total of that, including the valence electron of all atoms within the compound. Okay, so add them all up together. The second one is that when you are seeing hydrogen, always put hydrogen atom at the end or at the terminal. Okay, so the reason for that is because you already see that hydrogen cannot have more than 2 electrons. Therefore, it will not be able to form multi-bonds. It's going to be able to form only one bond. Okay, because it can contain maximum of only 2 electrons because of that. Okay, so number 3 is that when you are having several types of elements come together to make covalent compound, you are going to put the element that have the least value of the electronegativity to be on as a central atom. We are going to take a look at this later, why that would be, right? So we are going to look at the formal charges and how that is going to help us determine which one would be the best structure, right? So pretty much the summary of that would come into this number 3 right here. So the general idea is we're going to use the least electronegative atom to be the central atom. We're going to see later on why that is. Okay. Number 4 is that you are going to make sure that you distribute all the electron that you count from number 1. Okay, make sure that hydrogen would meet the duet, which means it needs to have 2 electrons, and all other main group elements would need to have the octet. Okay, so which means 8 electron total around it. Okay, and then lastly, you are going to start to form double bond and triple bond if there is any atom that lack of octet. Okay, so start with single bond, and then you are going to start to distribute electron, and then if that doesn't work, it doesn't meet an octet, then you are going to start with the triple bond and double bond. Okay, so what do we mean by that? Okay, so let's take a look at example 7. Okay, so example 7, we have ammonia, oxygen, and nitrogen gas. So ammonia contain nitrogen and hydrogen. Okay, so what I'm going to do is that, well, we already see that hydrogen should be the terminal, right? So that means what you are going to do here is that you are going to somehow surround this element with hydrogen first. But before we put anything in, make sure that you count number of valence electron total as well. Okay, so this is total. Oops, sorry. Okay, it doesn't total valence electron. Okay, so it's come from, okay, so hydrogen going to have 1 valence, right? Nitrogen would have 5. Therefore, in this case, you are going to add those up together, 5 plus 3 of the hydrogen. Add together, you're going to have 8 electron total. Okay, when you have 8 electron total, what you are going to do next is you are going to start with the single bond first, right? So you already have the skeleton right here by putting nitrogen in the middle and then have hydrogen to surround that nitrogen. So what you're going to do next is you are going to start connect each of these by bond. Okay, so this is called single bond. Okay, so one of this line called single bond is each single bond contain 2 electron sharing. Okay, so one is come from nitrogen, the other is come from hydrogen, sharing bond together, sharing those electrons together. Okay, this bond right here, again, this is called single bond. This single bond contain 2 sharing, each of these contain 2 sharing electron. Okay, therefore, in this case, if you count the number of electrons that we already spent, it would be 1, 2, 3, 4, 5, 6. We only spend 6 electrons. Okay, so we spend 6 electrons in the bond. Okay, so that means you are going to have how many left, right? So you are going to have what, 2 left, right? Because 8 is total, we already spent 6, we have 2 left. Where would those 2 go? Okay, so those 2 are going to go into the central atom to make sure that it's going to meet an octet. So that means those 2 electrons would go with the nitrogen. So right now total would be 1, 2, 3, 4, 5, 6, 7, 8. So 8 electron total, exactly what we have. And also hydrogen meet a duet as well. This hydrogen would contain 2 electrons, 1, 2. Same thing for this, right? 1, 2, 1, 2. So hydrogen meet a duet. So that's good. What about this nitrogen right here? This nitrogen contains 1, 2, 3, 4, 5, 6, 7, 8. So nitrogen also surrounded by 8 electrons as well. So therefore, in this case, this is going to be valid Lewis structure because hydrogen meet a duet rule and nitrogen meet an octet. Okay, so that's how you can come up with the Lewis structure. Okay, so the next thing that we are going to take a look at is going to be oxygen. Okay, so let's take a look at oxygen. So I'm going to start with counting total number of valence electron the same way that we did earlier. So oxygen is in group 6, so we have 2 of them, so 6 times 2, that's come out going to equal to 12 electron. Okay, so now since we have 2 identical elements, I'm just going to put them side by side. Okay, what I'm going to do is I'm going to start with single bond first. Okay, so if we start with single bond, we are sharing 2 electrons together between these 2. Okay, so you are sharing 2 electrons. So if you share 2 electrons, you are going to see that you still have 10 more to go, right? So what should I do? Okay, so I can start adding the lone as the rest of the electron as the lone pair. I can do that as well, right? So I'm going to go ahead add those as a lone pair. If I do that, Okay, so this is what I'm gonna have. So I already spent 2, I have 10 to go, so I'm gonna put 5 and 5 right here, right? So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, right? So that way total would equal to 12 electron, because the number of electron that we represent within the compound have to equal to the total that we have. It cannot have more than or less than. It have to be exact. Okay, so in this case, if you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, they both already have 12 electron. However, the problem with this Lewis structure is that each of these oxygen don't meet octet yet. Okay, so that means this is not going to be the correct structure. Okay, because they don't meet the octet yet. We need to make sure that they meet an octet. In order to make them to have an octet, okay, what you can do is that you probably see these two, right? If you connect them together, if you have these two to share electron, you're probably going to end up having the 8 electron between each of these, right? So I'm going to bring those 2 electron and then connect them. Okay, so now you can count. Total have to be 12, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Perfect. The overall electron are 12. But what about each oxygen? Okay, so each oxygen, this oxygen here contain 1, 2, 3, 4, 5, 6, 7, 8, right? Because they're sharing. So this oxygen would have 8 electron total. So that's good, because this oxygen meet an octet. Same thing for this oxygen as well, is meet octet as well. 1, 2, 3, 4, 5, 6, 7, 8. So therefore, this would be a good Lewis structure that represent oxygen molecule. Okay, so let me draw that a little bit better. So that would be those 2 dots here. Okay. And these 2 bonds that come together, okay, this is what we call double bond. Okay, double bond would contain 4 sharings electron. Okay, so 1, 2, 3, 4 is 4 electron sharing within double bond. Okay, all right, last one, nitrogen. Nitrogen contain total of how many valence electrons? So nitrogen is in group 5. We have 2 of them, so total would be 10 electron total. So I'm going to start with N and N side by side. I'm going to start with, again, the first bond, right? So we're going to make first bond first. If I do this, I already spend 1, 2. I spend only 2 electrons, so we have 8 to go. So I'm going to start to distribute those around the nitrogen. So 8 to go. So 1, 2, 3, 4, right? 1, 2, 3, 4. So that would be 8 total. So total would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So that would be total of the 10 electron. However, if you're looking at this doesn't make an octet yet, right? Because nitrogen contain only 1, 2, 3, 4, 5, 6. It's only 6. It needs 2 more. Okay. In order to make those 2 more, what we're gonna do is that we can start sharing these electron together. Okay, so what can you do is that we are going to share those electrons. Okay, so I'm going to make them, I'm going to actually write this a little bit clearer. We're going to share those electrons. Okay, so we're going to share those electrons. So remember, so I'm not going to make any bond yet, but it's still the same. It's just me write differently. So total will still be 10 electrons, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so the only thing I'm going to do differently is to connect these 2 together. Okay. So that way, in this case, the total number of electrons around nitrogen would be 8 instead of only 6, right? So in this case, if you count the number of electrons around this nitrogen here, it would be 1, 2, 3, 4, 5, 6, 7, 8. Perfect, right? That's already made an octet. Okay. This bond right here that have 3 lines, we call this triple bond. Triple bond contain 1, 2, 3, 4, 5, 6 sharing electron. Okay. So another thing I want to point out is that this pair of electron right here that you see of this I highlight in yellow, those pair of electron, those are what we call lone pair electron. Okay, so that means for ammonia is contain 1 lone pair. For oxygen molecule is contain 1, 2, 3, 4, 4 lone pairs electron. For nitrogen contain 2 lone pairs electron. Okay, so we count as them as a pairs, right? So these are lone pair. Okay. Lone pair are the one that they stay as pair and they do not actually share with any other molecule. It's going to be within that atom. Next, let's take a look at a little bit more complex structures such as dibromomethane and also ethylene and also acetylene. Okay, so how can we draw Lewis structure that contains several atoms like this, right? So pretty much you are going to need to make sure first that you count the number of valence electrons. So that's going to be the first step. Okay, so the number of valence electron of the dibromomethane would come from carbon, right? 4. We have 2 hydrogen, each is 1. We have 2 chlorine, each 7, right? So total will come out equal to 20 electron. Okay, so what we are going to do is that you will probably notice that carbon is the only single atom within this, right? All of this has 2. So what we're going to do is that we are going to put carbon as a central atom. We're going to see later on as well that carbon has less value of the electronegativity than chlorine. So that's why we put carbon in the middle as well. Okay, so in this case, we're going to draw skeleton first. Okay, so I put 2 hydrogen surround this carbon and also 2 chlorine surround this 1 carbon. Next, what you're going to do is that you are going to start with single bond. Okay, so I'm going to start with single bond. Remember, each of single bond contain 2 sharings electrons, right? So that means each of these bond contain 2 electrons. So total electron that we already spent would be 8 electron sharing. Okay, so all of these contain 8 electron sharing. So that means we have 12 electron left. What should we do with those 12 electrons? Okay, so you can start to distribute them. Okay, so should I put in hydrogen? The answer is no, because hydrogen is already have a duet. Okay, 1, 2, right? So hydrogen already have a duet. You don't need to add any more. If you add more, it's going to be invalid. Okay. What about carbon? Should I add more to the carbon? The answer is no. You should add the leftover electron to the surrounding atom first and then put into the central atom last. And also another reason for this is because carbon already have an octet, right? So 1, 2, 3, 4, 5, 6, 7, 8. So that means we don't need any more electron in carbon. The only thing that lack of octet would be these 2 chlorine, because right now these 2 chlorine contain only 1, 2 electron, right? So you are going to start distribute those 12 electron into each of these. So divide them by 2, right? So 6, 6, give them 6, 6. Okay, so overall, if you count the number of electron, overall this electron would come out equal to 20, right? So you have 8 plus 8, right? And then plus 2 plus 2, right? So that would be what, 18, right? And also hydrogen made a duet, carbon made an octet, chlorine also made an octet as well, 1, 2, 3, 4, 5, 6, 7, 8, right? So that means in this case, this structure would be the valid Lewis structure. All right, what about the second molecule? Second molecule contains 2 carbon and 4 hydrogen. So again, you are going to start with counting the number of valence electron total. 2 carbon, each carbon is 4 valence, right? Hydrogen 1 valence, but we have 4 of them. Total come out equal to 12. Again, we are going to put hydrogen as the terminal atom. Okay, so at the end of the atom. So we are going to pretty much surround these hydrogen atom around the carbon. Okay, so I'm going to do that. Okay, so I'm going to surround those 4 between these 2 carbon. And I'm going to do the same thing. Okay, start with 1 single bond, because that's going to be the easiest place to start. Start with 1 single bond, and what you are going to do next is count the number of electron sharing. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We already spent 10 electron sharing, which indicate that we have 2 electron left. Which one should get the 2 electron then? Should I put 2 electron like around hydrogen? The answer is no, right? Because hydrogen already have a duet. So what if I divide this into 1 of each carbon? Okay, that would work, right? So if I divide those two into this, so that means we already spent 12 electron total. However, don't forget to check whether the element is already have an octet or not, right? Because right now, yes, you spend all the 12 electron, but if you're looking at the number of valence electron around carbon, you will see that carbon, each of these carbon contain only 1, 2, 3, 4, 5, 6, 7. Is have only 7 electron, is not 8 electron yet. Okay. What you can do is what? If single bond doesn't work, then you are going to form double bond, right? So then that's what we're going to do. We are going to switch those into double bond. Okay, so pretty much we are going to switch what you have earlier, right? So either you distribute them like this, or either you put these 2 electrons like this. Either way, it's not going to one of the carbon will not mean an octet. Therefore, we're going to convert these pair electron into a double bond. Now, if you draw a double bond, you will see that this carbon now would contain 1, 2, 3, 4, 5, 6, 7, 8. It would have 8 electrons surrounded because the double bond contain 4 sharing electrons, right? So that means in this case, everything is satisfy the duet and octet rule. So this structure would be valid. Okay. All right. So same thing with the last one. You count the number of total electrons, come out to be 10. You're going to do the same thing. We have 2 carbon, right? 2 hydrogen. So hydrogen would be the terminal. And what you're going to do next is you are going to connect them with the single bond. If you do this, you spend only 6 sharing electron. So total that you will have left would be 4. So again, if you start with 4, you can put 4 in 1, or you can put 2 in here. But either way, it's not going to achieve the octet rule. So therefore, in this case, you will need to convert those into triple bond, right? Because if you convert this to double bond, it's still not going to achieve the octet. So you're going to convert that to triple bond. So if you convert this to triple bond, you are going to see that carbon would have octet, right? Both carbon, so 1, 2, 3, 4, 5, 6, 7, 8. And hydrogen also have a duet as well. So that means this structure would be the valid Lewis structure. So pretty much to summary what we just look at, right? You probably see that in general, hydrogen, right, will only form one single bond if you see all of these, because hydrogen are terminal atom and they are going to have to meet the duet. So that's why hydrogen would have only single bond. You cannot form double bond or triple bond for hydrogen. Hydrogen can only have single bond. Okay, and then the next general rules, this is usually but not always. What you are going to observe is that when you see carbon is have 4 bonds. Okay, and these 4 bonds can be a combination between single bond or single bond, or single bond and double bond, or double bond and triple bond, right? It's one of those, but total will come out it would have 4 bonds. Okay, and usually but not always for group 7A. So for example, in this group right here that I'm going to show you, so group 7A, most of the time it's going to form one single bond, but it's not always. There will be some exception later that we're going to take a look at. Okay, and then when you see oxygen, usually it would form 2 bonds. Okay, so either single bond or double bond, but it's not always. You're going to see this exception later as well. Okay, so this is just the general rule. Okay, so oxygen, give it 2 bonds, but it's not always true. Okay, so we're going to take a look at those examples when those exceptions will come play a role. And last thing that you might have to jot down is usually nitrogen would form 3 bonds, and it can be a combination of all of these as well, single bond, double bond, or triple bond. Again, usually, but there are also exceptions as well that we're going to take a look at. Okay, so again, what you will need to know is that these are true, always true. Okay, but this one right here would have some exception that we will take a look at in future videos. Okay, we're going to talk about those in the later videos. Here's the summary of what we just went over, right? So we pretty much look at the Lewis dot structure of just simple atom, right? Neutral atom, and those are, for example, like oxygen, right? So you just find out the number of valence electron and put a dot around that atom. And we're looking at the ionic compound. Ionic compound contain cation and anion. Cation doesn't have any dot, but it has the charge. Anion would have H dot surrounded with the charge as well, right? So we already look at those, right? So you notice that you don't indicate any bonds because they do not form bond because electron already transfer. Okay, and the last thing that we look at is the covalent compound, which means that their electron will share between each atom. So that's why we indicate them as either single bond, double bond, or triple bond, right? And the electrons that are not shared, we call those lone pairs. Now you should be able to start working on the paper homework 6.1 part B number 2 now. Draw the base Lewis structure for this compound. For now, do not worry about to provide the formal charges yet. We are going to go over these formal charges in the later. Next, we are going to take a look at the relationship between the type of bond, which is what we are going to call bond order, and their bond length, and also their bond energy as well. So the bond order that we are going to talk about is the type of bond that we see earlier: single bond, double bond, or triple bond. So for example, bond order 1 would describe the single bond, right? So for example, if you have carbon and carbon, it's going to be just one bond between these two carbon atoms. And the bond length is going to describe the length between the two atoms that come together to form this single bond. Okay, so pretty much the length from the nucleus of this carbon to the nucleus of this carbon, this is going to describe the bond length of this bond between carbon and carbon, and come out to be 1.54 angstrom. You don't need to memorize this number. What I'm expecting you to know is the relationship. Okay, so we're gonna see the trend after I show you all of this. Okay, so again, I'm just gonna, so this is what experimentally reported, right? So it's reported to be this length, and the bond energy is described the amount of energy that is required to break this bond. So pretty much if we want to break this bond between carbon and carbon single bond, this is how much energy in kilojoule of 1 mole of this bond would require, right? So if we talk about bond order 2, that would describe the double bond. Okay, so bond order pretty much is going to describe the number of bond. Okay, so the double bond, the bond length would come out to be for carbon would be 1.34 angstrom. So again, specific element would have different bond length, right? Because as we see earlier, different element would have different size. Therefore, when they form bonds, they are going to end up with different size of bond length. Okay, so in this case, the reason why I'm bringing this up because I know the value of carbon. Okay, so the energy that required to break the double bond apart, break this double bond apart, is going to be 614 kilojoule per mole. Okay, bond order equal to 3, that is going to describe the triple bond. Okay, so C, triple bond C, and the bond length of this going to be shorter. Okay, so 1.2 angstrom. Again, if you're looking at this, okay, so again, all of these are going to be for only carbon. Okay, if I'm talking about, like, let's say like nitrogen, right, those number would change. Okay, the triple bond, in order to separate these two atoms together or break this bond, the energy that required for that would be about 800 kilojoule per mole. What is my expectation exactly then? Okay, so I don't want you to memorize this number, but what I want you to know is the trend, right? The relationship between these three. Okay, so pretty much if you're looking at these three, you probably notice that as the bond order increases, right? So as the number increase from single bond, double bond, to triple bond, you will see that the bond length would decreases, right? So you will see that the bond length would decrease. So that's the relationship that I would like you to know. Okay, so this is applied for other element as well. Regardless of you changing these to other element, the relationship will still be the same. Okay, but the number here would be different, so that's why I don't want you to memorize the number. What I want you to know is the relationship. Okay, so if you're looking at the bond energy though, what happened to the bond energy as the bond order increase? You're also expecting the bond energy to also increase as well. So makes sense, right? So for example, if you have like 3 ropes versus 1 rope, right? So it's easier to break apart 1 rope. It's harder to break apart 3 rope, right? That's why it's going to require more energy. So pretty much in this slide right here, the take home message is that whenever that you see single bond, it's going to have the longest bond length and it's going to have the lowest bond energy. Whenever that you have, triple bond, you are going to end up with the shortest bond length, and you are going to expecting to have the highest bond energy. Okay. The bond within polyatomic ions are considered to be covalent bond because of these are contain non-metal that combine together. So again, bond within each of these atom would be covalent bond. However, when we are putting these together with another non-metal or another ions, those are going to form ionic compound. I'm going to elaborate more of this when we actually get into the ionic compound that contain polyatomic ions. But for now, whenever that we talk about the specific polyatomic ions, know that each of these atoms are going to form covalent bond, which means that we are going to make sure that they actually sharing electron between each of those atoms. So first off, what we need to know is to count the total number of valence electrons. So what we have is for ammonium ion, we have hydrogen, nitrogen, and for carbonate, we have carbon and oxygen, right? So the number of valence would be 1 for hydrogen, 4 for carbon, 5 for nitrogen, and 6 for oxygen. So I'm going to go ahead and count those number of valence electron total. Okay, so for ammonium ion would be 5 plus 4 hydrogen plus 1, right? Oh, sorry, times 1 because each hydrogen is 1. Now you also will need to account for the charge of the polyatomic ion as well. The positive 1 charge indicate that these overall ions is already lost 1 electron, right? So positive 1 means it's lost 1 electron. Therefore, in this case, this is the total, but it doesn't account for that 1 losing electron yet. Therefore, you are going to subtract 1 from that because negative 1 is indicated is losing 1 electron. This is the number of electron total for the valence electron total, right? So therefore, in this case, the number of valence electron would come out equal to 8 instead of 9. Okay, so it's going to be 8 valence electron. Okay, so same thing for carbonate as well. If you count the number of valence electron total, carbon would have 4. We have 3 oxygen, and each oxygen contains 6 valence electron. And you probably noticed the 2 negative charge right here. The 2 negative tell us that these ions right here gain 2 electron, right? So therefore, in this case, the number of electron total as you gain, right, is going to add 2 electron to it. Okay, so do not forget this. Whenever that you encounter polyatomic ion, you will need to always account for those charges. Okay, so this is a common mistake that several students made from the previous year that I taught. So just make sure that you know that those ions, right, will need to include whether it's going to gain or lose electron. Okay, so in the total number of valence electrons. So this one would come out equal to 6 times 3 equal to 18, right? So 18 plus 2, that would equal to 20. 20 plus 4, that's 24. Okay, so we have 24 valence electron. Okay, so what we're going to do next is going to be similar to what we did in previous slide, right? So pretty much you are going to go ahead, write out skeleton. So in this case, we have 4 hydrogen. So I'm going to go ahead, write out hydrogen surround nitrogen. If you count number of electron total that is already spent in here, it would be 1, 2, 3, 4, 5, 6, 7, 8 because each of those single bond contain 2 sharing. So we have 8 electron sharing total, which is exactly what we have here, right? The number of electron total here have to equal to what we have. And is this the valid Lewis structure? The answer is yes, because hydrogen have a duet and nitrogen have an octet, right? So 1, 2, 3, 4, 5, 6, 7, 8. So therefore, in this case, this is the valid Lewis structure. Because this is the valid Lewis structure, you will need to also indicate the charge of this polyatomic ion as well by using the bracket. Okay, so the bracket will tell us that this whole thing, the overall charge is positive 1. Okay, so this is the structure of polyatomic ion, ammonium ion. Okay, hydrogen and nitrogen are sharing electron, and because this overall lost 1 electron, it would have the overall charge of positive 1. Okay, next we are going to take a look at carbonate ion, I'm going to start with carbon. Okay, I'm going to start with 3 hydrogen, right? So, 3 oxygen, right? Oxygen, there are 3 of them, so I'm going to start with 3 of those. Okay, I'm going to start with single bond first. Okay, so I'm going to start with single bond. If I start with single bond right now, okay, so the number of electrons that I already spent would be 6, right? So 2, 4, 6. So I spend 6 electrons. Okay, so how many do I have left? So I have 18 left, right? So let me write. So that means in this case I have 18 electrons left. Okay, so 6 electron is in sharing. Okay, which is are in this sharing bond right here. So 2, 2, 2, right, so total 6. We have 18 left because 26 minus 4, that's equal to 18. Okay, so where would that 18 goes? Okay, so I'm going to go ahead, put them around the terminal atom first. So 1, 2, 3, 4, 5, 6, right, 7, 8. So 7, 8. So this is already have an octet. Okay, so another 1, 2, 3, 4, 5, 6, 7, 8. This is already have an octet. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. This is also have an octet. Now, if you count off these electrons that I just started to distribute, right? So 6, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 is equal to what we have left here, right? I just spent off that, right? So the overall of these come out together is equal to 24. However, this Lewis structure is not valid, is invalid, okay? The reason for that is because although all the oxygen have octet, however, the carbon that we have here is contain only 6 electrons. It has not meet the octet yet. So what you will need to do is that you will need to make sure that you switch one of these, right, to be a double bond. Remember, if single bond doesn't work, then try double bond. So I'm going to remove these 2 electrons to become a double bond. So if I do that, okay, so if I do that, I'm going to have a double bond between oxygen and carbon. And let's see if we have an octet yet. Okay, so I'm going to just convert those 2 electrons to be in this double bond instead. Right. So now if you count number of electron, okay, if you count still, right, so 1, 2, 3, 4, 5, 6, 7, 8, right, so 8 plus another 1, 2, 3, 4, 5, 6, 7, 8 plus 8, total come out to be 24. Carbon has an octet, right, so 1, 2, 3, 4, 5, 6, 7, 8. Oxygen, each of these oxygen also have an octet as well. Therefore, in this case, this would be the valid Lewis structure for carbonate. Okay, the only thing that is missing is going to be the charge. You need to indicate the overall charge of carbonate that is going to be equal to 2 negative, okay, 2 minus. So again, these represent the Lewis structure of the polyatomic ions that contain all non-metal that come together to share electron. And these ions gains 2 electrons. That's why the overall charge is have 2 negative charge. Up to this point, you should be able to start working on paper homework 6.1 part B number 3 now. Again, you are going to need to draw the base Lewis structure for each of these ions. Remember, we talked about the ions before, right, in the previous slide. So go ahead, draw those. Again, for now, just leave the formal charges for now. We are going to cover that soon. Okay, so just start to draw those Lewis structure. We just saw the Lewis structure of the polyatomic ion, ammonium, and also carbonate, right? In the previous slide, we know that within the ammonium bonds, the bond within this is covalent bond. Same thing for carbonate as well, right? So the bond within the carbonate ion is also covalent, which means that they are sharing electron together. However, if you think about why those become ions, to answer that is going to be because something else give or receive the electron from these ions, right? So that's pretty much that's what it's boiled down to. So we know that the ammonium ion is contain a positive charge, right? So we have NH4 plus, right? And then for carbonate is CO3 2 minus. So where are those plus and minus coming from? How the ammonium is losing electron and how the carbonate is gaining 2 electron. The answer is going to be what they are pairing up with. Okay, so in this case, because ammonium is pairing up with chlorine, is indicate that this one positive charge, which indicate that the ammonium is losing electron, is going to lose electron to chlorine. Okay, so that's what it tells us. So that means in this case, the chlorine would most likely to be Cl minus. Same thing for this one as well. The reason why carbonate is contain 2 minus is because when carbonate, right, paired up with calcium, the calcium is the one that is going to give off those 2 electrons to carbonate, right? So therefore, in this case, one is losing, one is gaining. That's why the overall, when you pair them together, you are going to end up having the ionic compound. So again, the bond between each of these polyatomic ions, the atom within the polyatomic ions is the covalent bond, but the overall, right, the bond of these two is going to consider to be ionic bond. Well, if we know this is ionic bond, what do we do? Well, because ionic bond, they do not share electron, but the electron already transfer, right? So it's already completely transferred from here to here, already transferred from here to here. Therefore, when you write the ionic bond, you have to separate them. We already see that from the previous slide. Therefore, in this case, what you are going to do is you are going to need to separate between these two terms. Okay, so one is going to be the ammonium structure that we just draw, right, which is NH4. We already drew that, okay, in the previous slide, +1, and you are going to separate this by parentheses and also indicate chlorine that has -1. Okay, so again, remember when we write out the ionic compound, we know that the cation will not have any, you don't need to include, so the cation would be, if it's just the metal, you don't need to include any lone pairs, right? If it's the polyatomic ions, you are going to draw the structure of the polyatomic ion and describe and then represent that. Okay. For chlorine, which is the anion, you are going to make sure this is, since it's single atom, you are going to include its valence electron, which is going to equal to 7, right? Because it's in group 7. But remember, it's except 1 electron from ammonia, right? So that's why chlorine become chloride ion. Therefore, in this case, the total number of electron on chlorine would equal to 8, right? Because accepting 1 more from this ammonia. Okay. If NH4 doesn't come with chlorine, then it will not be able to lose that electron. Lose that electron, so the ionic compound would not form, right? So in this case, it have to come as a pair. Okay, so this would be the Lewis structure of ammonium chloride. Okay, so this is the true structure of ammonium chloride, which is indicated by the ionic bond, right? Positive and negative charge come together. They are attracted to each other by the electrostatic force, right? The opposite charge force. So now what about calcium carbonate? You are going to do the same thing for calcium carbonate. We already see the structure of carbonate, right? So C double bond O, and then 1 oxygen here. Oops, actually I ran out of space, so let me rewrite that. Okay, so oops, I erased extra. So so for carbonate, okay, so this is the structure of this one. Okay, so for calcium carbonate, you are going to start with the carbonate that we already drew the structure. Okay, and each of these oxygen contain, so this top one contain 2 lone pair, this one contain 6 lone pairs. Again, we just went over this in the previous lecture, so don't forget the overall charge of this as well, right? So 2 minus, we already went over that. So again, these represent the covalent bond within the polyatomic ion, but the overall calcium carbonate is the ionic compound. Therefore, in this case, you will also need to indicate calcium 2 plus, right? That come from that. And because calcium lost 2 electrons to carbonate, therefore in this case, we just leave calcium as it is. Okay, so this would indicate the Lewis structure of calcium carbonate. Okay, which you will see that between cation and anion, there are no bond. They are going to attract each other by the force of the opposite charge. Okay, up until this point, you should be able to go back to homework number 1, part A, and start working on those Lewis structure of those ionic compounds. So again, these ionic compounds contain polyatomic ions, so which means that you will need to make sure that you know the structure of those polyatomic ions first before you put them together as the ionic compound. Okay, so similar to this example that I give here. The last part of this video that we'll take a look at is the formal charge. The formal charge is a fictitious charge assigned to each atom in Lewis structure that helps us to determine the best Lewis structure. So again, this is not going to be a true or real charge, because if you think about it, when we draw Lewis structure, especially for molecular compound, they do not transfer electron. Therefore, they do not have an actual charge, okay, because they are only sharing electrons. So in this case, we are assigning formal charge to just help us to determine the best Lewis structure when we draw. In order to calculate for formal charge, there are two ways to calculate for this. One is to count the total number of valence electron for that particular atom. We are going to look at the formal charge for a specific atom within the molecule. Okay, so the number of valence electron for that particular atom minus the number of lone pair electron. Okay, and then plus 1/2 of the bonding electron. Okay, so that's one way to do it. Or if you think about this, the half of bonding electron is pretty much the number of bond, right? So you can also use this as well. Pretty much is equal to the number of valence electron minus the number of lone pair plus the number of bond. What do I mean by that? Okay, so let's take a look at an example. So the example here, I have two examples, and these two are very similar. The difference between these two structures are the central atom, right? So this one have carbon as a central atom. This one has nitrogen as a central atom. We are going to take a look at which one would be the best Lewis structure, to put carbon as a central atom or to put nitrogen as a central atom. So we are going to determine that. Okay, so if you do so, you are going to start the formal charge with, let's take a look at the hydrogen first. Okay, so in order to count formal charge of hydrogen, you are going to take the number of valence electron of hydrogen, which is equal to 1, okay, minus number of the lone pair electron around hydrogen. There is 0, right? So there is no lone pair, therefore it's going to be minus 0. And the number of bond, right? So we're gonna, so if you distribute this negative into the parentheses, you will see that it's going to be minus the lone pair, also minus the number of bond as well. So we are going to minus the number of bond, which is 1 bond. Okay, so according to this, so the total formal charge of hydrogen would come out equal to 0. You can do the same thing for carbon as well. Okay, so also after you finish calculating these, the best way to represent this and is easier for everyone to see is write the formal charge right at the with the atom that you already calculate. On the exam, you don't need to show me how to calculate this. You can just show me the number that go with it. Okay, so for carbon, you are going to do the same thing. Valence electron of carbon would be 4. There is no lone pair, that would be minus 0. The number of bond, right? So minus distribute to into parentheses, that's going to be negative, right? So it's going to be negative 1, 2, 3, 4 because there are 4 bonds. So you are minus 4. Total would be 0. Now for nitrogen, you are going to do the same. Okay, so nitrogen has 5 valence electron, has 2 electron in the lone pairs. Okay, so this one is the number of lone pair electrons. Okay, so which means it's going to be the number of electrons in the lone pair. So we count them as the number of electrons, so 1, 2. Okay, we don't count them as a pair. Okay, so we count them as the number of electrons, and the number of bond would be 1, 2, 3. So minus 3. So total would be 0 as well. So the formal charge of nitrogen would be 0. You are going to do the same thing for this structure here. I would like you to pause the video now and calculate the formal charge for all of these, and we will take a look at your answer together. So let's pause the video now and then calculate the formal charge. All right, let's take a look at your answer. So if you calculate according to this formula that I mentioned, you are going to get the formal charge of hydrogen equal to 0 for this structure. For nitrogen, it would be 5 minus 0 minus 4, that's equal to 1, right? Because there is no lone pair electron. And then for carbon, it would be 4 minus 2 minus 3, and that's equal to negative 1. Okay, so that would be the formal charge of carbon. So now, how can we use formal charge to determine which one is the best structure then? So there are criteria for this. Okay, so before we actually determine which one is the best, what I would like you to note first is that whenever that you calculate formal charge, you will need to make sure if you have the neutral molecule, the summation of all formal charge of all element within the molecule need to add up equal to 0. For example, all of this add up to 0. All of this add up to 0. That means you calculate the formal charge correctly. Okay, so this is applied for neutral molecule. However, if you see the polyatomic ions or so pretty much ions that come in like with several elements, the summation of the formal charge have to come out equal to the charge of the ions. So which means that if it's not neutral, the summation of formal charge have to be the same as the charge of that ion. That's what it means. Okay, so since these two are neutral, right? So that's why they all add up together equal to 0, right? For each of these molecule. Now, how can we determine then which one would be the best? So there are two criteria that you will need to note. Okay, if you have the formal charge, you want to look for the formal charge for each element that closest to the 0. Okay, so if you're looking at this structure right here, the best Lewis structure would have all the element has the formal charge closest to 0, right? So all of these are 0. So this is better than this one because this one is not too close to 0, right? You have only one 0 and this is 1 and -1. So that means in this case, the first one would probably be better. Okay. And also, if you end up having, if you cannot find anything that close to 0 like this, if you end up having a like some other number that is there are non-zero number, you want to put the negative formal charge on the most electronegative atom, because if you think about it, the electronegative atom means if they have a higher value, it means they have higher ability to withdraw electrons. So it's make more sense to have the negative electron or negative charge on that particular higher electronegativity value, right? So if you're looking at this, the first one would fall into the first criteria. So that means in this case, the first structure would be the best Lewis structure. So this is the reason why when you have the different element for a molecule, you most likely to put the element that have the least electronegativity value in the middle, right, compared to that. The reason for that is because it's actually making the formal charge to be the lowest. Okay, so that's why this one is better. Okay, so now this is the general guideline that I mentioned earlier, why we put the least En atom as a central atom, because it's actually make the formal charge to come out to be close to 0 than those that you put the higher electronegativity in. Okay. All right. So up to this point, you should be able to start working on homework 6.1 part B, number 4 and 5. So number 4 and 5, what I am looking for here, okay, so to guide you through this, you are going to look at these polyatomic ions. You are going to draw 3 Lewis structure, okay, and each of those Lewis structure need to have different central atom, which mean the first one you are going to have what Cn like that, right? And the second one would be you're gonna put S in as a central atom. The last one you're gonna put N as a central atom, right? So it's going to be something like that. Okay. So remember, this one versus this one. Oh, sorry. These two are identical because it's just you just flip it, right? So you just flip that. You just flip the whole molecule, so it's still considered to be identical. So you just have to pick one. Okay. So I'm just going to pick that one because they are identical. So that means the Lewis structure of these polyatomic ion. There are 3 possibilities. One is carbon as a central atom, second one is a sulfur, and the last one is nitrogen. And after you draw these, put all the valence electron in, put all the bond in, right? So the next thing is to do number 5. So after you set up this Lewis structure, then you are going to look up number 5 and answer it, right? So to answer this, you are going to calculate formal charge for each of these molecule. Sorry, each of these atom. Remember, this is polyatomic ions, okay? Therefore, the summation of formal charge need to come out to be the same as the charge. So that means in this case, whenever that you add the formal charge for all of these elements together, it need to come out equal to -1. It need to come out equal to the charge of the overall charge of the polyatomic ion. Okay, so that's the note of it. And what you are going to do is that you are going to, after you calculate formal charge already, right? So this is what is going to come out at, right, after you calculate for all elements and add them together, it's going to come out equal to -1 in this case, okay? And what you're going to do next is you are going to determine which one is the best Lewis structure out of these three, right? Which one should be the best central atom, okay? So what you're going to do is you're going to use these two criteria right here to help you determine it, okay? So every atom have to be close to 0 for formal charge. And if you end up with the formal charge, it is like negative formal charge, it's not like 0. You are going to put the negative formal charge into the most electronegative atom. Okay, so you can see the list of these on page 63, right? So you can see the value of the electronegativity on page 63 to help you to compare. Okay, so that's it. So but that means question number 4 and 5 will help you to understand why we put a certain element as a central atom. Okay, so this just help you to understand that better. And after you already learn about formal charge, you should be able to start working on the rest of the part B now, right? Which is number 2 and also number 3 as well, because you already learned how to draw Lewis structure for this, but you have not learned about at that time you did not learn about the formal charge yet. So now after you know how to calculate the formal charge, I would like you to go ahead and calculate formal charge for those. Okay. All right. So this is the summary of this 6.1 part 1 video. So pretty much we talk about how to draw Lewis dot structure for all of these. Okay, we're looking at the relationship between bond order, bond length, and bond energy as well. And at the end, we're looking at formal charge, and we use the formal charge to determine the best Lewis structure based on the formal charge on each element within the molecule. Okay, so again, so pretty much start working on part 1 now. Okay, so that way you can get this out of your way.